Hello and welcome to another video by Hendog Maths, and today we're going to be looking at some physics actually that does involve maths. We're going to be looking at the forces that are acting on an inclined plane, so basically slope. So I have a box here, and the box is on a slope uh, with an angle of 30 degrees from the ground. That's important. And I've just labelled some forces already. As you can see, colour coded, we have the normal contact force. That is normal or perpendicular to the slope. We have the force of the weight of the box, which is mass times gravitational field strength, or mg. So I have that label, that's going straight down. And we have friction, which I will be talking about in this. And the coefficient of friction is a fifth, or 0.2. So that's how much friction there is. The mass is 5 kilograms of the box, and I'm assuming gravitational field strength is 10 meters per second squared. So I'm going to try and get the acceleration of the box sliding down the slope. And to do that, I have a equation here. Resultant force, I've called that F subscript T, is equal to mass times acceleration. It's Newton's second law of that. So acceleration is resultant force divided by mass. Here I've got some equations that force of weight is equal to mass times gravitational field strength, mg, and friction force is equal to Fn, or the normal contact force, times the coefficient of friction, or mu. So what I actually want here is I want some more forces labelled, and what I'm going to do is I'm going to resolve or unresolve actually this force of weight here, because it's not perpendicular to or parallel to anything, so I can't actually deal with it with the other forces yet, but I can split it into a horizontal and perpendicular vector relative to this slope here. So actually it can be two forces, one which is opposite but parallel to normal contact force, one which is perpendicular to normal contact force and opposite friction. This will be the net force, the resultant force. It will be the force which actually pushes, because the box will go in this direction. Okay, and I need to know what these are. And to do that, I'm going to need to know some things. First of all, let me just label this angle to be theta as well. It's a poor theta, 30 degrees, as this. And I don't want to go into too much detail, but if I've got here the triangle here, this would be the same triangle as here if I was to draw an imaginary line here, and we got a triangle going on there. And the reason this is 30 degrees quickly is that if this was a triangle, this would be 90, that's 30, so this is 60. If this is 60 and this, because this is perpendicular to the slope, this has to add up to 90 degrees. I've already got this at 60, so this one here has to be 30 degrees by default, the same as this. So then I've got a triangle here, as I said before, like that, involving, this is parallel to this force, so this I can just assume is this force. I've resolved it, I've moved this force down here just to get a triangle. So this one is here, and this force is here. This forms a right angle, and the weight force is actually the hypotenuse of this triangle, the one I've already got. And that is mass times gravity, so just label this side mg. I've also labelled adjacent, hypotenuse, and opposite, and the rules for sine and cosine of a right angle triangle, which we've gone through. Opposite over hypotenuse, adjacent over hypotenuse. So knowing that, mass times gravity, I'm actually going to say that mass times gravity, which would be 5 times 10, that'd be 50. Okay? And what I'm wanting is these two sides here, and to work them out I'm wanting the adjacent and the opposite sides. So with these equations I have here, I'm going to times both sides by the hypotenuse. You rearrange it to get opposite and adjacent by themselves. So sine theta, sorry I'm writing here, times hypotenuse, which is mg, so times 50, is equal to the op. And similarly, cosine theta times 50 is equal to the adjacent side. Not very nice right there, but That's what we've got it. We know what theta is. It's 30. And sine 30 is a half. So half times 50 is 25. And cosine of 30 degrees is root 3 over 2. Not that nice. So we can say that's 25 times root 3. So I'm going to say that's 25 root 3. So the cosine. Okay, so now I know these forces. So I know this is so this is my adjacent side. So this is 25 root 3, and this is my force, of which the box is actually going in the direction of, and that is just 25 newtons, as we worked out, which is good. Now, normal contact force is equal and opposite to this force here, 25 root 3. So that also must be 25 root 3. It can't be any more or any less. That's the point of it. And so they cancel out. So it's just friction and this force we have here, 25 newtons. So for the actual resultant force, the final force, after they've all cancel each other out, that is the force the box will be acting on the box. That we need to take away the friction force. So the friction force is normal contact force times the coefficient. So we know that's 25 root 3. So I'm just going to put it there. So 25 root 3 times a fifth, which is how we get the friction force. That would be 5 root 3. So that's our friction force. Okay, 5 root 3. So what we just need to do to work out the resultant force is we do 25 right here minus 5 root 3. And that's resultant force. Should have wrote here actually. Never mind. Now, of course, I've rearranged F equals ma to get A is equal to this, 25 minus 5 root 3, all over the mass. Just divide this all by 5, and that is our acceleration. So, just using rules, I can say that is 5 minus root 3 meters per second squared. And I'm just going to leave it in that form. I don't want to work that out. But that is the acceleration of this box. So hope you enjoyed this video on physics on inclined planes, and hope to see you in the next video.